We will record class today. Can't forget to do that. Okay, so let's see here. Moving on to chapter 2, we are. I don't know if I actually created a quiz for today. Yes, I did. How about that? All right. All right, well, let's go ahead and do a quiz, shall we? So, has anyone in here not dealt with vectors before at some point in your career? You've all dealt with vectors at some point? Okay. Well, then we'll go ahead and give you this quiz. Actually, I don't know if I opened it before. I didn't open it before. Show questions on the screen, show results as they come on the screen. Okay. Open student input. So we have this first question, which of the following quantities is a vector? Ugh. What a weekend. You guys all have a good weekend?
Yeah.
Good. Oh, there's Matt. Oh, no, that's Lane. But Matt's back too. All right. How was yours? My weekend, it was busy. I got a lot of things done though. That's good, I guess. I did some more time building. I'm building an addition on my house.
Is that the exam?
Bathroom right now. Build the shower. What's that? Sorry.
Is that the exam on the screen you're sharing?
Yeah, it's the quiz.
Quiz.
The pre-quiz for chapter 2, the vector chapter. Have you done anything with vectors before, Lane and Matt?
I think so.
So, okay. Matt, how about you? Have you have any experience using vectors?
Not that I can remember.
Not that you can remember. Okay, we'll take a stab at it and see how you feel about it. So far we have, well, it looks like everybody's answered. We have, somebody has answered.
Oh, wait.
Oh,
yeah, okay, I didn't read all the answers.
Somebody has measured 5 meters, four people have answered 5 meters north, and one person has answered 10 meters per second.
I was the one who answered southwest. I didn't see the north at the end of 5 meters. I messed up.
Okay, well, that's fine. So why do you think that the 5 meters north would be a better answer than just southwest?
Because it vectors more than just speed, it's also direction.
Okay. So anybody agree with that assessment? It's true. So 5 meters north doesn't have any speed with it either, actually. It just has a distance, maybe? What did you say, sorry? A magnitude and a direction, or some kind of value and a direction? Okay.
50 meters per second north also be a vector?
So we have, sorry, which one?
5 meters per second north, wouldn't that also be a vector because it still has a magnitude?
Yeah, which one? Well, we have the 10 meters per second. Do we have a 5 meters per second north? Or are you saying if we added per second into 5 meters per second?
I'm just saying, does the meters or meters per second matter in both ends of the magnitudes that should be combined with that direction?
What do you guys think? Should it matter what we're measuring? As long as it has a magnitude and direction. Okay, we have some people kind of just staring at me like, well, are you going to tell me the answer? Some people kind of nodding and agreeing with that. Right? Can anybody define a vector for me in such a way that we can resolve the answer here? What is a vector? Somebody kind of said it before. Something with a magnitude. And so what's a magnitude?
Measurement.
A measurement, okay.
I don't know, it's not force, but it's just.
But force for how much? So it's an amount.
Yes.
Okay, so a magnitude is an amount. It's some measure of something. Okay, I can get on board with that. And we should have a direction involved as well for it to be a vector. So it has to have an amount and a direction. Okay. When I was a freshman at Brigham Young University, I took a class, which probably you all have to take in some form or another. I took a class called linear algebra. And it's actually the mathematics of multiple dimensions, essentially, is what it is. So anything from one dimension up to hundreds of dimensions or more, any kind of number of dimensions you want. And it's a very complex mathematical study, actually. It's actually something that that has been around for a very long time, but didn't really start to get studied in great detail until the 20th century. Einstein was probably the first to study it in great detail, and then others have studied it in many different ways since. And in order to do mathematics in multiple dimensions efficiently and effectively, you really do need to do it with vectors, because you have many things that you're doing calculations with all at once. For example, you'll have mathematics that involve your position in X, Y, and Z. So you have a coordinate that says I'm at 5 in the X direction, I'm at 3 in the Y direction, I'm at -2 in the Z direction. But you can do that two different ways. You can either treat them all separately, or you can treat them all at once as a group, mathematically. And that's what linear algebra does, is it treats them at once as a group. And so in that case, it actually treats coordinates as a vector. And in fact, it will treat any number as a vector, any value as a vector at all. And it doesn't necessarily have to have a direction, as long as it's a number that can be treated using the system. So while in physics, we do consider vectors to be values that have a component that is all about the size of the vector, we usually call that the magnitude. And then there's something about it that also indicates direction. Sometimes that's a north, south, east, west, sometimes it's up, down, sometimes it's just a sign, positive or negative, right? We usually in physics and in engineering consider that to be the case, but you may come across a situation where in fact, you will come across situations where a vector doesn't look like that at all. If you take calculus 3, for example, is anybody taking calculus 3 right now? If you're taking calculus 3, you're going to learn that vectors don't necessarily look like number and direction. In fact, they will look very different in many ways, not just in what they have in them, but the way they're actually written down will look very different. And so it's important as you're going into engineering to be able to kind of roll with the punches in math and physics and engineering, because there's so many different ways that things are represented, the way they're defined, particularly when it comes to mathematics, because mathematics is not truly any kind of science. It's a language for understanding science. It's a language used to describe nature. And many mathematicians would disagree with me on that, because they tend to treat it as a science, I suppose. But the problem with trying to treat mathematics as a science is that the first step in all of science is observation. And that never happened with mathematics. Nobody ever observed math and then tried to understand it from there. We created math to understand what we were observing. We didn't observe the math first, right? So there's no real observation that started math. And that's the big quandary, whether or not math should be considered a science. I consider it a language. So whenever we're dealing with math, and vectors is the use of vectors is a way of utilizing mathematics to represent things that we see in the natural world. And whenever we deal with mathematics, there will be variations on how that can be done, how it is represented, how it's used. So be aware of that, because you will encounter it over and over and over again in your life as an engineer and as a scientist in general. So my answer to this question would be, all of these could be vectors if we wanted them to be, because they all can be treated like values that have some meaning. But in the physics sense, we usually consider a magnitude and a direction, and that would be the 5 meters north, right? But it could also be 5 newtons west, or it could be 53 furlongs per fortnight negative, or something like this, whatever. However you want to define your magnitude and your direction is whatever you want to do. But usually it will include, a vector will include a magnitude and a direction. In this class, we will use some very specific methods or standards for writing down vectors. But we will have some variations here and there to give you an idea of how it's done in different places, different ways, and in different situations. So don't worry about your score if you didn't get this exactly right. I will adjust quiz scores for participation. The most you will ever lose in a quiz is 1 point per question out of 10 total points. So if you miss both questions in this quiz, you get 8 out of 10. So question 2 is this one here. We're going to add 2 vectors together, and we want to know what is the correct diagram that shows how vectors add together. Now, again, if you've not done this before, just kind of take a stab at it and we'll talk about it. Okay, we're still waiting for one more answer. There we go. All 6 results received, and everybody agrees that it's A. Why would we all say it's A? Because it looks pretty good.
That's what it looks like when you add this on the 2 vectors.
Because you've done this exercise before, right? That's actually as good an answer as any, because when we are doing mathematics, we are often doing things the same way as everyone else so that we can communicate well, right? However, I mean, I wouldn't say it's as good an answer as anything else, but it's a pretty good answer. Maybe a slightly better answer would be, let's think of this in terms of a vector we just talked about in the previous problem. The previous problem, our vector was like 5 miles north or something like this, right? Or whatever it was. It was some distance and some direction. Well, let's say that let's use that as our type of vector. We're going to have a distance and a direction. So let's call this one 5 miles a little bit north of east, right? And we'll call this one 5 mile, or this one's a little longer, so we'll call it 8 miles, a little bit east of north, right? Well, if we actually move those distances, if we actually walk along those vectors one after the other and add the two movements together, because those are definitely kind of movement things, right? Then our overall position at the end would be represented by this third vector, which would be the sum of those two. Because we did them one after the other, it's like adding them together, kind of, right? So that is a fairly good representation, where this one is not, because this one doesn't show us moving this one and then this one. It says we moved this one and then we went back to our original position and then we moved this one, right? We went this movement. And this one shows
Wouldn't
them,
that like,
sorry, go ahead.
I was about to say with B, wouldn't that end up with them subtracting the orange line?
Yeah, so
If they're going in,
this one would maybe represent some other different kind of operator between the vectors. Maybe it's subtraction, maybe it's something else. It also may represent two different people going two different directions, right? But it certainly doesn't seem to represent doing one motion and then doing the other motion, which is what we think addition is usually, right? Addition is 3 and then you have 5 after that added to it, right? Or whatever, where addition is not 3, then go back to 0 and then 5, right? So, and this one also shows the same as part A, except it shows that our beginning point would be at the end of our motion and we'd go back to the beginning point for the sum. So that one doesn't necessarily make as much sense, right? So vectors are not just these things that we have definitions for in our head. They actually have real life representation, and there's meaning behind the way we manipulate them. There's a purpose to it in the real world, right? Which is what we really want in all of our science. We want everything that we do in science to have a purpose in the real world. I actually I've had many experiences with this. I've had lots of coaching experience. I coached swimming for 5 years in California many years ago. And we started, me and my best friend who were the coaches for this team, we started with a team that was the bottom of the league, rock bottom of the league, and had hardly any swimmers on the team. We had, I think, 60 swimmers on our team. And for that league, that was 100 less than the next biggest team, the next smallest team, I guess you could say. But anyway. So we went from the bottom of the league to winning the league championship for 10 years running, which went 9 years after I had already left. But we went from the worst of the worst for probably 20 years. And we took this team in 5 short years to the best team in the league for 9 years after I left. And I actually visited the team on the year, either the last year that they won it or the first year that they lost it. I went back and visited, and a couple of my swimmers that I had coached were coaching the team at that time. And one of the swimmers that I had coached that 10 years earlier, and who was only 12 years old at the time, was now in his 20s and was swimming against Michael Phelps in the national Olympic qualifications. So we did a really good job. I'm not saying that to brag. I'm just saying we knew what we were doing, and we did it well. And one of the reasons that we did it well is because we decided that the things that we did in practice were going to always have some translation to a race. We never did things that didn't have some purpose, some connection to how you race in the pool. So every little thing, and not only did we do these things that had some connection to racing, either physically or mentally or technically or something else, but we told our kids, especially the older kids who were really coming into being highly skilled swimmers after years of working with us. But not only we told them these things because we wanted them to understand, so that when they were doing them, they were thinking about what they were trying to accomplish for their race, right? And vectors are that way in physics. I did the same thing when I coached volleyball for about the same number of years here at the college when I first got here. And I did the same thing there. When I first got there to coaching, the team was doing all kinds of weird things that I couldn't understand why they were doing them. In fact, they were doing things that were directly countermanded things you wanted to do in a game. For example, they would do this drill where they would hit the ball on purpose to somebody on the other side. They would specifically try to hit it to somebody, which is exactly what you don't want to do in volleyball. That's basketball where you're trying to pass to a person. In volleyball, you want to hit where there is no person. You want it to hit the floor. And this team had an incredibly hard time scoring the ball because they were always hitting it to the opposing players because that's what they were used to doing in practice. They were trying to keep the ball going as much as possible in practice. I'm like, there's no point. In volleyball, you don't want it to go. You don't want it to keep going and going. You want it to hit the floor as soon as possible. So we changed that drill and we had incredible success for the 5 years I was coaching. Before I came, they'd been to nationals once in 20 years. While I was there for 5 years, they went to nationals 3 times in 5 years and could have gone all 5 years. They were really close every year I was there with coaching. So it's the same thing, and it's the same thing in everything. If there's a purpose to what you're doing and you understand that purpose, you're going to succeed better. So understanding the purpose of the mathematics, understanding the purpose of vectors, it's going to help you use them better. It's going to help you to understand why we're using them better. So that's all I have to say about that. So let's go ahead and move on to our chapter 2 today. So chapter 2 is about vectors. We start off with a discussion about scalars and vectors. We call the magnitude of a vector, we often call it a scalar quantity. And there are many scalar quantities that are not the magnitude of vectors, but a scalar quantity is really exactly what it says. It's something, it's a number that scales something. It gives scale to it. So it gives it size, right? Magnitude is another way of saying that. So if you're talking about your shoe, my shoe size, the scale of my shoe is 10.5 inches. That's because I'm wearing size 10.5 shoes, right? So that's the scale of my shoes. That doesn't tell you anything about the shape. It doesn't tell you anything about the height or the style of shoe or anything else. More information would give you a vector, right? It doesn't necessarily have to be a direction, actually. More information is, just more information, and then you would require another way of representing that. If you're talking about, the distance to Kearney from North Platte, you have 100 miles being the distance, and you could actually give that some vector character by saying it's, roughly east, but 100 miles is a straight line distance, right? So that's the scale of the distance, the scalar quantity. Anyway, then vector quantity is, of course, being something that has more than just that scale to it. And a vector you could maybe have a size vector that is for dogs that is defined as the tail of the dog to the head of the dog, to the nose of the dog, or something like that, right? And if you define the length of a dog as the measurement from the tail to the nose, and that's the direction of it, then all of a sudden it becomes a vector, right? Usually vectors have a very specific definition. There is such thing as a position vector, for example. Can anyone guess how we define a position vector? I'll give you a clue. A position vector requires that we have a coordinate system. So where do you imagine the position vector starts and where do you imagine it ends?
So the origin point and the location.
It starts at the origin and ends at the location. Plain and simple. It's an arrow that has what we call the tail of the arrow, or the tail of the vector, which is the part that doesn't have the arrow. And that starts at the origin, and then it goes to the position, which is the head or the arrow end of the vector end, right? So position vectors are vectors that can be defined in many ways. You can define them using many different methods, I suppose, mathematical representations. But the simplest is just a pair of coordinates. You just, 5, 3. X is 5, Y is 3. And that tells you where the head of the vector is. And you always know for a position vector that the tail is at the origin. And you're good to go, right? So. We also write the magnitude of a vector. When we're writing a vector, let's say that we call the vector D, we use an arrow over the vector to denote that it's a vector when we're writing it by hand. In this book, they'll just use a boldface print instead of putting an arrow over every vector. So they'll forego the arrow and just use boldface print. If you're talking about the magnitude of that vector, D, then we use the same letter, whether it's capital or lowercase, but we don't use boldface. We call that the magnitude. And we also use this notation to denote the magnitude of a vector, where it's kind of the absolute value bars around, and then you put in the boldface vector on the inside. That's also showing the magnitude of the vector, or showing that we're taking the magnitude of that vector. So those are some ways that we describe and denote vectors. This is an interesting picture here. Here we have, how do I get rid of this search thing up here? I want to get rid of the search bar. Can I get rid of it? I don't know if I can. I need a bigger screen. I used to have a bigger screen, but this computer has a small screen. So we'll live with it, I guess. We will shrink the screen, or go to a, I don't know if I can go to it. I can go to a bigger one. I can't go to a smaller one. There we go. That's better. Almost, not quite. That only shrunk the text. It didn't do anything for me. Didn't do the picture any. Didn't change the picture any. Anyway, okay, so going back to our picture here. You can see here that we've got this vector that goes from our tent to this lake. And this vector is going to be what we call a displacement vector. Displacement tells you a beginning point and an ending point, right? And so the beginning point is the tent, the ending point is the lake, but there are many trails to get to the lake. And each of these trails has a much different length than the displacement vector, because displacement vectors are always straight line distances between 2 points and a direction. But distances aren't always that way. So the vector is different than the distance. The displacement vector is different than the distance. And the distance is a scalar. Whenever we talked about how far did you go, let's say that I drove to Kearney, and you say, and I say, well, I drove 100 miles to Kearney. Well, that's pretty much the straight line distance between here and Kearney. It's pretty close to that. So you know that I went straight to Kearney. However, if I said I drove 400 miles and I went to Kearney, you would really have no idea where I went, because I could take all kinds of 400-mile journeys to Kearney. There's so many different highways and byways and county roads and different things and cornfields I could drive through and everything else, right? There's so many different things I could do to get to Kearney using 400 miles up on my truck. Not sure my car could take all those journeys, but my truck could handle them all, I'm sure. So that's an important thing to recognize, is that some things are only scalars, and distance is one of them. Distance, you never say I went negative 30 miles. You always say I went 30 miles, because distance is always a scalar. It's always positive. So. Vectors are often considered parallel or anti-parallel, or linear and collinear or anti-collinear. When vectors are parallel, they are pointing in the same direction. And that means they can be along the same line, in which case they would also be collinear. So collinear vectors are also parallel vectors, but collinear ones are pointing exactly along the same line. Parallel vectors can be separated from each other, but still pointing in the same direction, like these two vectors here. These two are collinear. These two are just parallel. These were collinear and parallel. These ones here are anti-parallel and anti-collinear, but you can also have anti-parallel that look like this, where one of them, where if B was pointing upward and to the right and A was pointing downward to the left, would also be anti-parallel because they're pointing opposite to each other. You can have equivalence of vectors. The warning about equivalence of vectors is that they don't necessarily have to be right on top of each other. They just have to have the same length in the same direction to be equal vectors. They have to have the same units, which is really the same length as well, right? So one of them can't be 4 meters per second north and the other one be 4 meters north. Those are not equal because their units are not equal, therefore their lengths are not equal, right? But if they're both 4 meters north, then they're equal vectors. It doesn't matter where they start from, where they end from, they're always where they end at. It just matters how long they are in which direction. You can also have vectors that are exactly the opposite of each other. So 4 meters north, 4 meters south, or 4 meters per second north, 4 meters per second south. Those are two vectors that are equal in length if you're only considering the magnitude of their length, but they're opposite in direction, right? And then they have orthogonal vectors, which are 90 degrees to each other, right angles to each other. And orthogonal is a word that actually means independent, okay? So why would we use the word orthogonal for vectors that are 90 degrees to each other? What makes them independent? What makes a child independent of their parents? Doing its own thing, okay. Well, they could cross. We just have to move them. Vectors are pretty movable. They're not necessarily fixed in space except for position vectors.
Does orthogonal have to be 90 degrees or does it just have to be not 180?
So it can be 90, it can be 90, it can be 270, but it can't be any other angle, really, unless you want to go into 4 dimensions. Even then, you could still argue for 90 degrees, but in a different way. No, the 90 degrees is important in our Cartesian system. So does anybody know why Cartesian is named, why it's named, what it's named?
So it's not Cartesian, but I'm pretty sure it's not named after a country.
No, it's actually named after a person from France. So so it's the guy's name was Descartes. You ever heard of Descartes, the philosopher? He was a French philosopher during the Renaissance. And like many philosophers, he was sitting around one day bored. Because philosophers, that's how they come up with great ideas, is they sit around being bored. And he noticed a fly buzzing around his room. And he thought to himself, you know, with 3 measurements and 1 piece of information, I could tell anybody where this fly is in my room at any given point in time. What are those 3 measurements and 1 piece of information that he was talking about? We've already talked about it, actually.
X, Y, and Z, and one piece of information is the vector from that you get measurements.
Yeah, so the origin, right? So what he needs, what he needs to tell somebody is the origin that he measured from, and then the distance in 3 separate directions. Why are they separate directions? Why are they independent? When we do X, Y, and Z, we usually do X in the horizontal direction and Y in the vertical direction, right? If you move in the horizontal direction only, if you're only moving in the X direction, will your Y direction change? Will your Y position change? No, because they're orthogonal. When you're moving purely in X, Y doesn't change because because Y and X are 90 degrees to each other. That's why 90 is so valuable and so important. Now you think, well, duh, but believe it or not, people really didn't necessarily think that way when they started using things for 90 degrees. The Egyptians weren't necessarily thinking like that. They weren't thinking about that when they built the pyramids on top of a square. The square was just a convenient and strong thing. They could actually measure 90 degrees. They figured out how to measure 90 degrees. They couldn't figure out other angles. 90 degrees was an easy one. Tie a rope off with 10 knots, fold it into a 3x4 triangle, and you get 90 degrees at the corner. Simple. That's how they figured it out. But other angles are not that way. If you take off, if you put your y-axis at 30 degrees, while you're moving along your x-axis, you will also be moving along your y-axis, because your y-axis is pointing somewhat in the same direction as x. It has a little bit of x pointing to it, right? So orthogonal means that they're independent, that if you're moving in the direction of one, that you're not moving in the direction of the other. If you're purely moving in the direction of one, you're not moving in the direction of the other. So that's what orthogonal means. And all of our coordinate systems that we use for practical purposes are orthogonal coordinate systems. Descartes was the one that came up with the idea of the orthogonal coordinate system with the fly in his room. Okay. There are other coordinate systems that we use that you may not think of as orthogonal, but they are. For example, the polar coordinate system, which has in the XY plane, it has the angle and the distance out from the center. Have you ever used that one before in trigonometry or calculus or something? Well, that one is also orthogonal, because the one coordinate, which is the R coordinate, that one points outward from the center and rotates around in some direction. And the angle that you measure is measured at 90 degrees to that. It's measured this way. So that's 90 degrees. That's your first coordinate is outward. The other one is always 90 degrees to it. However, that coordinate, that angle coordinate, is always changing its direction depending on which way your R is pointing. But it's always 90 degrees to R. And then Z is 90 degrees to R as well in the other direction. There's even the one that we use on the Earth's surface, longitude and latitude, right? Those two are 90 degrees to each other. Everywhere a longitude line and a latitude line cross, it's 90 degrees. The next time they cross, it's that cross, that 90 degree cross, is pointing a slightly different direction, but it's still 90 degrees. Right? It's because it's on the surface of a spheroid. So anyway, when we're doing simple geometric adding of vectors in one dimension, you just line up the vectors one after the other if you're adding them. If you're subtracting the vectors, you remember that subtraction is just the addition of a negative. So you can just flip one of them around, flip the one that you're subtracting around and stack it on top. So this is what it would look like if you were adding vectors D from A to D and then D from D to B. They should have named them something different like A and B or something, but whatever. So they're essentially adding this purple vector and this orange vector by just stacking them together. And then the resulting vector, which is this one here that goes all the way from A to B, it starts at the tail of the first one and ends at the head of the second one. Now, if you want to subtract a vector from B to get back to this point C, then you can just add on the negative of it if you want. So whatever the difference vector is here, you could add the negative of it. So it'd be pointing in the opposite direction. In this case, they're adding on, let's see, I don't know what they're doing here. They're going back for a tackle box, they say. But anyway, here they're adding this one and then adding this one and then subtracting. That one looks too small to be the subtraction. I should probably read the story. I don't know what the story is. Stopping to rest at point C to point B, going back for drop tackle box, finishing up at the fishing pond. Yeah, still doesn't make sense to me. I guess this is their first one. Oh, so this red one is their first movement, and then they go back. So that's this one. So if you add this one, this red one to this green one, that's like subtracting the green one from the red one, right? Because the green one's in the opposite direction, so that's like subtraction. And then you would get the purple one, and then you would add the orange one to get the total, which was the blue one. They should stack them up in a row from like top to bottom or something, but so that it makes sense what the movement is. The problem with adding vectors like this is that you have to draw them extremely precisely to get a right answer. Like if you were actually trying to add together these vectors and one of them was 4.2 miles and the next one was 3.9 miles and whatever else, you would have to scale that down and you get out some graph paper and rulers and draw them extremely accurately, get an extreme amount of precision and accuracy so that when you were done, the length of your vector actually represented the answer, right? And so we don't generally use this geometric or this pictorial version of vectors except to just explain kind of how things work to give us some visual aid. Anyway, multiplying vectors, if you multiply a vector A by 2, for example, then you get a vector that's twice as long, pointing in the same direction. If you multiply a vector by -2, then you get a vector that's twice as long, but pointing in the opposite direction. Same thing if you multiply by half or a third or -0.7 or whatever else. Multiplying by a negative will always flip the direction of the vector. Multiplying by some number out in front will always scale the vector by that number. So if it's a number less than 1, it's going to give you a smaller vector. If it's a number greater than 1, it'll give you a bigger vector. And that's the representation of that. Here they're showing a way of representing vectors here that is often used when people are learning how to use vectors, where you have this D sub AD. So these subscripts down here are usually going between 2 points, one point called A and one point called D, where the first one is the point you start at and the second one is the point that you end at. So this is a notation that's often used when first learning vectors, but it's not often used when you're learning vectors, when you're using vectors, because it's just too many things to write. We also represent vectors in this book using boldface. At the beginning, they're going to put a little arrow over it like this, but we won't do that. We won't see that later on in the book because it just takes too much time. However, when you're writing vectors, you should use an arrow so that you can keep track of what is a vector. Just put a little arrow over your vector, over your whatever name your vector is. Then you know it's actually a vector quantity. And there will be many reasons to do that. You definitely want to keep track of your vectors. If it's a capital D without the vector sign or the boldface in the book, then that means that it's just talking about the magnitude of that vector or the actual length of that vector, right? So that's the difference there. In vector arithmetic, adding is commutative, just like it is in regular old number arithmetic, right? So A plus B equals B plus A, whereas, and it's also associative, so you can add whatever you want first and then add something else later. You don't have to do it in any particular order. If you're multiplying by a scalar and adding the scalars together or the scale vectors together, it is also distributive, so this distributive law also works. Okay. However, multiplying by vectors is a whole different deal. You don't want to take that and just translate that from what you know about multiplication into vectors. For one thing, there's different kinds of vector multiplication, different types of it. For another thing, vectors are just a little painful to multiply. So you don't want to just try it out. We will do it though. Here is one way of showing a vector writing a vector down. You have the vector D. You've got the arrow over the top. You've got the boldface. It says it's going from point B to point A, and then it says it's equal to a magnitude, which is the 6 kilometers. It also has a direction in there. The negative is actually part of the direction. So the magnitude would be 6 kilometers. The direction is negative, but it also gives us a thing, this boldface U with the little hat over the top. We usually call that U hat or U unit vector U. A unit vector is a vector that is equal to 1. So U has a a magnitude of 1. And that's why we can put it here, because if you multiply any scalar by 1, it doesn't change the scalar. So we haven't changed the -6 at all by putting that u there, right? But the u will usually denote a direction. It will usually be associated with a particular cardinal direction in your coordinate system. When we're doing x and y, u is equal to I or j for either x or y in physics. In engineering, not always the same. In engineering, sometimes they use different letters for I and j. It's depends on the engineering, but you'll get used to it. It's just the way it is. Sometimes people will use x hat and y hat to just make it simple, but that's certainly not the way it's done in engineering. So, so just so you know, that u is a unit vector pointing in a cardinal direction. It's either pointing in the x direction or the y direction or the z direction, depending on which direction your vector is pointing. And it has a length of 1 so that it doesn't affect the vector. You can tack it onto any vector pointing in that direction, and it doesn't affect any of the scalar quantity of the vector. So here we're going to do a quick example with vectors, the ladybug walker. So the ladybug's going to take several different little trips. We're all in one dimension. The one dimension is called the u direction. So we have positive u hat, and we have negative u hat, and then we have all these scalars on these vectors. So first we go positive 15, then we go negative 56, then positive 3, then positive 25, and then negative 19. And in this case, in one dimension, it ends up just being back and forth, because it's just one dimension. It's along the line, right? So this ladybug goes through these different movements back and forth. And to figure out where the ladybug ends up, you just add them all together, because you can always add together vectors that have the same unit vector associated with them. These ones all have u hat associated with them, so you can add them together, just like normal numbers. You cannot, however, add two vectors together that have different unit vectors. If one of them has a u and one of them has an I, you can't add those together without doing some manipulation. So they do that. 2 dimensions is a bit more complicated, but the idea is still the same. Here we have 2 vectors in 2 dimensions now. So now they're not collinear, they're not parallel. They're pointing off at different angles. That's 2 dimensional. Because now we have to consider x and y if we're considering the plane of the page to be x and y like normal. If you have a and b here, you can add them together. You add them together by putting them head to tail again. Now they don't really show that here, but if you imagine taking b here and sliding it over to the head of a so that it's right here along this dotted line, you can see where they would be head to tail, and the resulting vector would go from the tail of the first one to the head of the second one. You can see how that would work, I think. Right? For subtraction, it turns out that if you put them tail to tail, you can actually draw the subtraction vector by going from the head of the second one, the one that you're subtracting, and going to the head of the first one. And this D here would be the difference between A and B. So A minus B essentially. B minus A would go the other way, from the head of A to the head of B. But you can still do that graphical kind of pictorial representation of vectors. But again, using it would not be very practical, because you'd have to not only get the lengths of your vectors perfectly scaled, but you'd also have to get the angles perfectly right, which would be even harder than getting the lengths right. So it's not terribly effective using these methods to do our math, but it can be done, and it is done often. With computers, it's much it's a great help. One of the times that they do this a lot is in flight plans for airplanes. Airplanes generally try to travel in straight lines from airport to airport, so their flight paths are kind of like vectors, right? But the thing with airplanes is that you have a lot of things affecting the airplane as it flies along. Specifically, you have wind that's affecting it. That's the big deal. That's the biggest thing. Wind affects airplanes. So as you're flying along, the wind is blowing your plane in a different direction than you're flying, usually, because you don't always fly with the wind at your back, right? Or with the wind coming straight at you. And so you have to be able to add the direction you're flying to the direction the wind is blowing. When you add those two together, that resulting vector will tell you where you're going to end up. So if you're flying from Tallahassee to Jacksonville and your plane is pointing in the direction of A, but the wind is pointing north, you're not going to hit Jacksonville because A goes directly from Tallahassee to Jacksonville and you're getting pushed north by the wind. You're going to end up north of Jacksonville somewhere. So you actually have to fly a little bit south of Jacksonville so that the wind will push you into Jacksonville, right? On longer flights, if you're flying north and south, well, actually, even if you're flying east and west, but if you're not flying exactly east and west, then the curvature of the Earth, or the rotation of the Earth, more to the point, the rotation of the Earth will actually change where you're going as well. So that starts to be an issue. If you're going directly east or west, it'll just change how long it takes you to get there. But which is important also, because you usually only put enough fuel on your plane to get you where you're going with a little bit of extra for safety. You never want to carry too much fuel because it takes fuel to carry fuel. You have to burn fuel to carry fuel, so it makes it less efficient. It also makes it more dangerous to have more fuel. So that's vectors are often used in all these things with planes. It used to be that they had to draw these things out by hand, but now, of course, they have computers that can do the vector work for you. This search bar is going to drive me crazy. I'm going to figure out how to get rid of that dumb thing. Goodness. Do I have to skip? But anyway, making me crazy. All right, so anyway, that gets us most of the way through section 2.1. And you should be able to get started on the homework with that. We're going to move on to 2.2 and the rest of the chapter. We have, well, we actually already did coordinate systems, and we talked a little bit about components of a vector, but we're gonna do more components of a vector next time. That'll get us more into two-dimensional vectors as well. And then we'll be learning how to do math with vectors instead of as arrows, as components. So we'll learn how to do algebra, and then we'll do math products of vectors. Finish up on Wednesday. So we'll see you on Wednesday. Have a good day today and tomorrow. Arrivederci. Make sure if you have questions that you send me a message. I'm sorry? Yes, so I actually did mail all the kits or send the kits. For those of you in McCook, you'll have to pick up your kits at the college, and I should send everybody an email about that. But for those of you in McCook, you have to pick up your kit at the front office of the college. I haven't yet built the kits for you guys here yet, but I will get that done. I'll probably do that starting this afternoon after my classes, and then finishing up Tuesday. So I will get those to you. Oh, is it due tonight? I'll move that to like Thursday. I'll move the lab to Thursday.
I got a question though. Why are you not wearing shorts and sandals?
You'll be disappointed by the answer.
What's the answer?
The answer were the pants were the first thing that I looked at in the morning. And I grabbed them and put them on.
Sorry.
I don't really do much thinking about the clothes.
Yeah,
I have like a stack of polo shirts that I just grab the first one that I touch. And I don't even turn on the lights in my closet sometimes.
This got time to think about.
I know, I'm just like, I just grab the first one that I touch. And then I usually just grab the most convenient pair of whatever I've got to put on the bottom. And my clothes, this is how much I don't think about clothing. I bought these pants for $1 at my favorite secondhand clothes store is down by the library. because I can find Levi's which fit the best for me and last the longest for $1.
That's pretty nice.
Yeah, because normally they're like $70 or $60. They're so expensive. When I was a kid, they were like 25. But anyway, but they last forever and they're comfortable and everything else. And I can get shorts for about the same and polo shirts. So all my clothes are $1 at that place. They don't always have my size, but I check it regularly. The only thing I buy new are shoes because I buy them to play volleyball, and then when I use them when I wear out for volleyball, I use them to wear every day. And that's how much I care about my clothing. I pay $1 for them. I buy socks and underwear new.
If it works. If it
Yeah,
works.
socks and underwear I buy new. That's it though. Everything else I buy used. If people are going to throw away pretty much new clothes, I mean, these are a little long, so I fold them up, but I don't care. I'm like Einstein. Einstein's wife, I'm not smart like Einstein at all, but I dress like Einstein. Einstein's wife got so sick of him wearing weird, mismatched clothing that she went and bought him an entire closet of clothes that all matched, all fit, and were all new. She would just cycle out the old ones all the time. So he never had to think. He just went in and grabbed things and put them on, and they always matched. And they always fit him, and they were always new. Like, that's me. I just have a closet full of clothes.
Thinking about other more important things like physics and engineering.
I'm not really sure if that's it. I'm just lazy, I think. I'm just like, I don't want to spend time doing that. See you guys. Wayne, did you have any questions before we're done?